All right, let's talk about alcohols as a functional group, not as something to do at the weekend. Alcohols are where we have the hydrocarbon, one of the hydrogens has been replaced with an oxygen, and then that oxygen is then bound to a hydrogen. So we have an OH group, and we call that OH group a hydroxyl group. The oxygen within an alcohol is actually sp3 hybridized, so it has four substituents around it. It has the carbon that it's bound to, it has the hydrogen that it's bound to, and then it has two lone pairs. So overall it's tetrahedral, it's just the lone pairs occupy the space, but they don't have an atom at the end that the oxygen is attached to. So each of the bonds that the oxygen makes in an alcohol are forming sigma bonds. So there's a little typo here, that should be a sigma. Let's do that again. So that should be a sigma bond. So the oxygen is involved in two sigma bonds, one to a carbon atom and one to a hydrogen atom. Alcohols are really common industrially, in nature, in pharmaceuticals, all sorts of places. So obviously ethanol, I'm sure you're familiar with. It's the alcohol that's in alcoholic beverages. Methanol is poisonous, and we hope that it's not in your alcoholic beverages. Ironically, the sort of cure or treatment for methanol poisoning is ethanol, because they compete for the same enzyme. Propanol, propan-2-ol, I should say, isopropyl alcohol is also known as rubbing alcohol. Terpyl alcohol is a commonly used organic solvent. Ethylene glycol has been used as an antifreeze, so you add it to water and it depresses the freezing point. Glycerol or glycerin is a trial, and that forms the sort of one of the subunits for fatty acids within living organisms. And cholesterol is a complex alcohol. It's got this steroidal structure, but it has an alcohol functional group within that structure. To name an alcohol, we simply get the backbone of the molecule and we put ol somewhere within the name, and we give it a number to say where that alcohol, where that hydroxyl functional group is. And if there's no higher priority substituent, then we start numbering at the alcohol or at the end of the chain nearest the alcohol. So for example, for this molecule here, we start numbering at the carbon that has the alcohol attached, and then go out along the longest chain. So it's a 6-carbon chain, so it's a hexanol, and the alcohol is at the 1 position, so it's a 1-hexanol or a hexan-1-ol. So either of those is okay. You can put the number either before the part of the name that tells you how long the chain is, or you can put it between that part of the stem and then the ol that signifies the functional group. For some reason I prefer this one. I just think it looks neater. It's a bit easier to say maybe, but they're both allowable. Now, if we're naming compounds that have other functional groups, then there's an order of priority, and it turns out that halogens are lower priority than alcohols. So this gets named as a 2-bromo-1-propanol, and the same with alkenes. So this is named as a 1-ol, and then the alkene starts at the 2 position, so it's a 2-butene-1-ol. The other important thing to know about naming alcohols and recognizing their structures is that we can classify them as either primary, secondary, or tertiary. So a primary alcohol has, at the carbon attached to the oxygen, we have one R group. So one alcohol or non-hydrogen substituent and 2 hydrogens. So it's a primary, and we give it the symbol 1 with a degree sign. A secondary alcohol has 2 R groups and only 1 hydrogen, and then a tertiary alcohol has 3 R groups and no hydrogens attached to it. So this is at the carbon that is directly attached to the oxygen. And whether it's primary, secondary, or tertiary has a big bearing on its properties and its reactivity and so on. So if we can recognize what type of alcohol we have, then we can say something about the types of reactions that it will do. So there's a big difference in reactivity between primary, secondary, and tertiary. And we'll come to this in a moment where we talk about how easy it is to form a carbocation from these species and how easy it is to do SN2 type of reactions. Now, when we look at alcohols, one of the important features of the structure that gives them their properties is the fact that oxygen is very electronegative compared to carbon, and particularly compared to hydrogen. So the oxygen-hydrogen bond is very polarized, and so we have a delta minus on oxygen and a delta plus on hydrogen. And this gives rise to one of the most important properties of alcohols, in that they can form hydrogen bonds, where the hydrogen of one molecule can form a weak interaction with the oxygen of another molecule, and that tends to influence their properties, like the boiling point and so on. They also, compared to alkanes, they're much more soluble in water, and they have higher boiling points and melting points. So for example, methanol is infinitely soluble in water, whereas ethane, which is very similar in molecular weight and in shape, is insoluble in water. And the boiling points are drastically different because of that hydrogen bonding that's keeping those molecules from getting away from each other and into the vapor phase. So the boiling point of methanol is 65 degrees, but the boiling point of ethane is minus 89 degrees, so a huge difference. And we can look at the trends. So ethanol, similarly soluble in water, propane is not soluble in water, and so on. So even as we get to quite long chains, pentan 1-ol is soluble to an extent of 2.3 grams per 100 grams of water, whereas hexane is still insoluble. Now, alcohols, we can have more than one alcohol functional group within an organic molecule. And if we add more than one, we get more opportunities for hydrogen bonding. And so the water solubility tends to increase, and the boiling point tends to increase as well. So if we have two alcohols in a similarly sized molecule, so we have butane 1,4-diol, the molecular weight is about the same, the number of electrons is about the same, so the boiling point is almost 100 degrees higher than the monoalcohol. And the water soluble is now back to being infinite, so the diol is infinitely soluble in water. And this really links into some of the properties of one of our favorite sugars, which is sucrose, which is from cane sugar and other sources. And many other carbohydrates that we call sugars, they're polyols. They have many hydroxyl functional groups, so they have many alcohol functional groups. And those alcohol functional groups mean that they're incredibly soluble in water, and often to very high extents, or even infinitely soluble. So how do we make alcohols? There's quite a number of ways. One of the simplest ways is that we take an alkene and we treat it with water and an acid. The acid protonates the alkene to give a carbocation, and then the water attacks that carbocation, then we lose a proton, and we end up with an alcohol. And we can do that with a variety of alkenes. It's much faster with alkenes that can form a stable carbocation. We can also do it via nucleophilic substitution reactions. So if we take an alcohol halide and we treat it with water, under the right conditions we can generate the alcohol and hydrogen bromide in this case. We can do it with primary alcohols. So this was a tertiary alcohol, and it happens rapidly. If we do it with a primary alcohol, we'll normally need a better nucleophile. And so instead of water, we need hydroxide, which is a much more powerful nucleophile. And so we can do this with sodium hydroxide at room temperature, and we get the bromide displaced by hydroxide to give the alcohol. Another way to synthesize alcohols is to reduce carbonyl compounds with appropriate reagents. And probably the most common reagent is this one here, which is called sodium borohydride. Okay, it's a reagent that's reactive enough to react with ketones and aldehydes, but is still stable enough to be used in an organic chemistry lab without any particular precautions. It's fairly stable towards air and moisture and so on. So if we treat an aldehyde with sodium borohydride, we get a primary alcohol. If we treat a ketone with a similar reagent, lithium aluminium hydride, then we get a secondary alcohol. So, and this is because ketones have two R groups attached, whereas aldehydes only have one R group. And so we can only get primary from aldehydes and secondary alcohols from ketones. There's many reactions of alcohols. We can oxidize them to make ketones. We can react them with carboxylic acid derivatives to make esters, we can oxidize them to make carboxylic acids. We can partially oxidize them to make aldehydes. We can react them with electrophiles to make ethers. We can dehydrate them to make alkenes. And we can halogenate them to make alkyl halides or haloalkanes. So one of the important reactions of alcohols is that they are actually weakly acidic. They have a pKa of around 16, and that means that you can pull off that proton with a suitable base. Now, it's not quite an acid-base reaction, but a very easy way to make an alkoxide, which is the conjugate base from an alcohol, is to treat it with sodium metal. So this is actually a redox reaction. It generates hydrogen as a byproduct. And you can see here is a lump of sodium that's been put into a test tube that's filled with alcohol, probably ethanol. And you can see bubbles coming off that, and that's hydrogen gas coming off the sodium metal as it reacts with the alcohol. Once you've formed the alkoxide, the conjugate base of the alcohol, it's a potent nucleophile and a strong base. So I'm sure you're familiar with the reaction of sodium metal with water. When sodium reacts with water, we give off hydrogen and we generate sodium hydroxide. And that's a really vigorous reaction. So it'll be hot enough to generate a flame and can be quite dangerous with large amounts of sodium. The reaction of sodium with alcohols is a bit more controlled. It depends on the alcohol. So methanol reacts very fast with, ethanol quite fast, and then more and more hindered alcohols, the reaction is slower and slower. Other alkali metals, such as potassium, also react with alcohols, and as we go down the periodic table, the reactions tend to be more and more vigorous. So the potassium alkoxide can be formed from potassium metal and the alcohol, which also gives off hydrogen gas. So the most common alkoxides that are used in the lab are sodium ethoxide, which is formed from treating ethanol with sodium metal, and potassium butoxides. That's formed from tertiary butanol being treated with potassium metal. So they're both commercially available, or you can make them in the lab yourself. Now, on the other side of the spectrum, alcohols are also weak bases, so they can be protonated by a strong acid. So under acidic condition, we can form what's called an oxonium ion. So the alcohol can attack the acid to form a new OH bond. And so now we have a group that has got an oxygen with two hydrogens attached and a formal positive charge. Now that group is a really good leaving group because when we break that sigma bond between the carbon and the oxygen, push electrons toward that oxygen, we're kicking out water as the leaving group. And water is a nice stable molecule. It's neutral, it's stable, and so it's a nice molecule to act as a leaving group. Much better leaving group than OH minus, which is hydroxide, which is much less stable because it bears a negative charge. So if we can form this oxonium ion, we can quite often break the carbon-oxygen bond, kick out water as a leaving group, and generate a carbocation. And that process will be determined, the rate of that process will be largely determined by the stability of that carbocation. So if it's a tertiary carbocation, in which we've drawn an example here, then that tertiary carbocation is relatively stable, and so this is a fairly facile process. Okay, so we can convert alcohols to haloalkanes through a nucleophilic substitution reaction. There's two main processes to do this. One is treatment with a hydrogen halide, which is a strong acid, and that's particularly common if we have a tertiary alcohol or some other alcohol that can be converted to a carbocation fairly readily. And overall, that process, we lose water and form the new carbon-halogen bond. If we have a primary alcohol or an alcohol that can't form a carbocation readily, we normally do it through a slightly different process and often using other reagents such as this one here, thionyl chloride, that I'll talk about more in a moment. So here's some examples. If we take cyclohexanol and we treat it with hydroiodic acid, then we'll end up with the iodine in place of the hydroxyl group. And so we'll generate iodocyclohexane and water as a byproduct. If we treat 1-propanol with hydrogen chloride, under suitably forcing conditions, we can get the primary alcohol chloride. But this type of reaction is much less common than secondary and tertiary alcohols. So relative ease of this type of reaction is tertiary are by far the most reactive, secondary alcohols are next, and then primary alcohols are fairly unreactive under these conditions. For tertiary and some secondary alcohols, it occurs by an SN1 mechanism, whereas for primary alcohols, it would basically always occur via an SN2 mechanism because primary carbocations are so unstable. So let's look at the mechanism in more detail. We take the alcohol, we make it attack the acid to form a really good leaving group, which is this oxonium ion. The oxonium ion then in a second step, we have breakage of this carbon-oxygen bond, kick out water as the leaving group, and we form a carbocation. We form that relatively quickly if it's stable. That's still the rate determining step. It's quite slow. As soon as that carbocation forms, it reacts with whatever nucleophile we've got in solution. And so if we've used, for example, hydrochloric acid, we'll have some chloride anion, and that can come in as the nucleophile, and we generate the alkyl chloride. The SN2 process is going to occur over two steps. Firstly, we protonate the alcohol to make it into a good leaving group. So we have this oxonium ion again, but instead of then departing and generating a carbocation, we get attack of the nucleophile at that carbon and breakage of that carbon-oxygen bond, kicking out water as the leaving group in an SN2 process. So this is the slow rate determining step in this particular reaction. So differences in the mechanism and the rate of these reactions really arise due to electronic factors and steric factors. So electronic factors are there electron withdrawing groups or other electron donating groups near the position that's undergoing reaction? And steric factors are there groups that are bulky near that position undergoing reaction? So if we have an SN2 process, then bulky groups near that position undergoing attack will slow down the reaction. And so this normally happens with primary alcohols that are unhindered. If we have a tertiary alcohol, it's going to be so hindered we don't get the SN2 process. So we go via SN1 mechanism, and then if we have groups that can further stabilize a positive charge, the carbocation, that will further increase the rate of the reaction because we're stabilizing that carbocation intermediate. As I said earlier, a more elegant way to make haloalkanes from alcohols is through a dehydration with other reagents. And thionyl chloride was the example I used earlier. So thionyl chloride with a primary alcohol will convert that quite smoothly to the alkyl chloride. We can also use other reagents such as phosphorus halides. Phosphorus tribromide and phosphorus pentabromide are common reagents to convert alcohols into the corresponding bromides. And there's also phosphorus chloride related reagents that will do the same thing. Okay, let's change tact and look at phenols, which are a subclass of alcohols. So they're still closely related to other alcohols. They're actually still an alcohol, but they have slightly different properties that make them interesting to look at as a different subclass. So phenols are where we have the OH group directly attached to the benzene ring, So they're an important class of organic compounds. They're really common in nature, and they're really common in natural products from nature that have biological activity. We can have phenols within molecules that are present in wine. So this is gallic acid, and this over here is catechin. These sorts of molecules are found in fruits like grapes, and they're found in tea, and they're also found in wine. And we can get molecules built up as polymers of gallic acid and other phenols that really impart some of the flavors and tastes within wine. So we can get those tannins that people talk about with wines that give them particular mouthfeel and flavor. The largest single use of phenol itself, which is just a benzene ring with the OH group attached, is in producing polymers and resins for plywood and for automotive uses. So the reason why we look at phenols as a distinct group from other alcohols is that they have different properties. So phenols are much more acidic than other alcohols. So if we treat phenol itself with hydroxide, we get it essentially completely converted to the corresponding conjugate base, and we call that a phenoxide. On the other hand, if we treat cyclohexanol or other alcohols with hydroxide, we get almost we get very little of the alkoxide formed. And that's because the pK of a phenol is around 9 to 10, whereas the pK of simple alcohols is around 16. So why is that the case? Well, when we generate that anion, it's stabilized by resonance. So the conjugate base of phenols is stabilized by resonance. We can draw a resonance form where we just push arrows around the benzene ring. But we can also draw resonance structures where we push the electrons from the oxygen into this position here, and then push the electrons onto the aromatic ring itself. So that means there's a resonance form where the negative charge is here. There's another one where we push that further out and the negative charge is here. And there's another one where we push it further and it goes on to this position here. And we know that resonance structures can make molecules more stable overall. So the more resonance forms we can write for a molecule, the more stable it is. So these variety of resonance forms stabilize the phenoxide, and it's particularly important because we're stabilizing a negative charge. Wherever we can smear out a negative or a positive charge across more than one atom, that leads to enhanced stability, because nature abhors having a charge within a very confined space. One other thing to note about phenols is that acidity can be affected by substituents on the benzene ring in much the same way that substituents can influence the acidity of carboxylic acids. So if we put an electron withdrawing group onto the benzene ring, then we can influence its pKa. So methyl groups are not very electron withdrawing, so in going from phenol to cresol, paracresol, we really don't get any change in pKa. Chlorine is a little bit electron withdrawing. It's at the para position here, so it's not terribly close, but it can still stabilize that negative charge in the phenoxide, and so we get a -1 pKa unit reduction when we go to a chloro group. I don't like these arrows here. I think they should be drawn like this. This shows you sort of a dipole. Nitro groups are really good electron withdrawing groups. They really stabilize negative charges through induction and also through resonance effects. So if we put a nitro group onto the para position of phenol, we get a drop in the pK of 3 units relative to phenol. If we put 2 nitro groups on, one at the para and one at the ortho position, we get another 3. So there's -2 there from parachloro, -3 from the mononitro, and then finally we can add 3 nitro groups to phenol, and we get a pKa of around 0.5. So this is a very strong acid. It's actually quite similar to something like trifluoroacetic acid. So that compound, 2,4,6-trinitrophenol, has a common name of picric acid. And it's got a lot of uses in organic chemistry. And in the past, it used to be very commonly used to make salts. By treating a base, like an amine, with picric acid, you can make the picrate salt. And they were often used because they're often crystalline and you can make solid derivatives of a basic molecule. Unfortunately, picric acid and picrate salts are often explosive, and so its use has declined a lot in recent years. Okay, so hopefully that gave you a bit of background in the structures and the reactivity of alcohols and phenols. Thanks for watching.